Okay, so we shall continue our discussion on quantum statistics. That is, now we have been talking about Bose-Einstein statistic to start with. So we have seen the distribution law, how does it happen for the Bose-Einstein statistics. Now we will talk more on that. So in this lecture, we are going to start with a numerical problem just to recap our understanding on Bose-Einstein distribution law. Okay, then we'll talk about the degeneracy in Bose-Einstein gas. Then so this the degeneracy part we have started talking about before starting the quantum statistics, and I said that this going to be the prerequisite for what is coming up. So that's we are going to really see the effect of degeneracy in this lecture. Mainly to start with, we'll see the how does energy and pressure of the Bose-Einstein gas deviate from the perfect gas, which we call it degeneracy, right? Okay, then we will talk about another very interesting and important topic regarding the Bose-Einstein statistics, that is Bose-Einstein condensation. Okay, so to begin with, let's look at the numerical problem. Okay, so it is given here that 5 bosons are distributed in 2 compartments. Okay, so I have 2 compartments to start with, let's say. Okay, and so 2 compartments, there are 3 cells in the first compartment. Okay, there are 3 cells in the first compartment, and there are 4 cells in the second compartment. So what all we have to calculate? Find a number of ways of distributing 5 bosons in 3 cells. Okay, so meaning it could be in the first compartment. Okay, so I have total of 5 bosons. So we have seen in the previous video that how to calculate the number of ways to distribute Ni bosons in Gi number of cells. So the number of ways is given by this particular equation that we have seen. Okay, so this is Wi, which gives you the number of ways to distribute. Ni is the total number of bosons to deal with, and then Gi is the number of cells present in a compartment. So nothing we have to do, simply we need to substitute. So we are doing for the problem the first part of the problem. Okay, so we need to find out for Wi. So Ni is 5 here because we have to deal with 5 number of bosons. So 5 plus Gi how many? 3 cells, then minus 1, so this many factorial divided by Ni is what? 5 factorial, G minus 1, so that is 2 factorial, right? So this will end up giving me, so 7 factorial, okay, divided by 5 factorial, 2 factorial, which is 6 by 7 and divided by 2, so which is going to give me 21. Okay, so there are 21 ways to distribute 5 bosons in 3 cells. Okay, so let's look at now the second part of the problem. Okay, let me clean this up. Okay, so the second part of the problem, so the first one we have done. So the find thermodynamic probability for a macro state 5, 0. Okay, so thermodynamic probability means what? So the number of microstate for a given macro state. So the macro state is given here 5, 0. Okay, that means the 5 bosons are there in compartment 1. Okay, and so all 5 of them are here, and 0 meaning there is no bosons in the compartment second. Okay, so this is your first compartment, this is your second compartment. Okay, so number of microstates for a given macrostate is given by this expression regarding the boson or Bose-Einstein statistics. Okay, so here W will be equal to, so this is product will go from where? I to K will be equal to 2 here, isn't it? Because there are only 2 compartments. Okay, so again Ni is 5, so 5 of them, so 5 is your number of particles, number of bosons in the first compartment. Okay, so the 5 minus, and in the first compartment how many cells are there? There are 3 of them, right? There are 3, so 3 minus 1, this is factorial divided by 5 factorial, and then Gi is 3 minus 1, 2 factorial, then multiplied by, in the second compartment how many particles are there? 0 factorial. Okay, plus Gi, so Gi, number of cells in the second compartment is 4, so 4 minus 1 is 3 factorial. Sorry, I have done something wrong. Okay, you should not be doing this. So I should have, sorry. Okay, so I should have done, okay, so this is 0 plus, so this is 4 minus 1, 3 whole factorial, I should have written. So then 0 factorial and then again 3 factorial. So see, this part is going to give you 1, right? So 3 factorial by 3 factorial, everything is going to be 1. So again we are ended up with what expression we had for the first problem. So this is going to give me 21, right? Okay. 7 factorial by 5 factorial into 2 factorial. So same, so answer will be the same for the first and second part. Okay, now come back to the third part. Okay, so third part, what do we have to do? Calculate the number of microstates in the macrostate 4,2. Okay, see, this is the asking same question but in a different way. Okay, so the language is different. Okay, so again you have to use calculate this W, right, number of microstates or the thermodynamic probability. Okay, so what I have to do, this is, I can write, this is like 4,2. Okay, so here 4 bosons are there in the first compartment and 2 are there in the second compartment. Okay, so 4 plus, so 4 particles are there in the first compartment and how many cells are there? 3 cells are there. So 3 minus 1, this is factorial, divided by 4 factorial and 2 factorial, right? 3 minus 1. So multiplied by, in the second compartment there are 2 particles, 2 plus Gi is how much? 4, so 4 minus 1. Okay, this is whole factorial divided by 2, then again 4 minus 1, that is 3 factorial. Okay, so on top here I will get 6 factorial divided by 4 factorial into 2 factorial. Here we will get 6 minus 1, so it will be 5 factorial divided by 2 factorial, 3 factorial, right? So equal to, here will be 5 cross 6 divided by 2, and then here 4 plus 5 divided by 2. So I will get, this is 3, this is 2, so this is 15, so then I will get 10. So I will get answer to be 150. Okay, right? So the number of microstates in the macrostate 4,2 will be 150. Okay, so I hope you got the idea how to calculate this number of microstates or number of ways to distribute, particular number of bosons in particular number of cells present in a compartment. Or so you have to, if you have to calculate the total number of microstate or thermodynamic probability, you have to use this expression. So the number of ways to distribute in each compartment, you have to multiply. Okay, so this, you can carry out another problems for yourself and to have a better understanding of this. Okay, now let's get back to our discussion, right? So the degeneracy in Bose-Einstein gas we are trying to understand. Okay, we are trying to discuss in this lecture. Okay, so the deviation in behavior of Bose-Einstein gas from that of perfect gas is called degeneracy, and this we have started in our last to last video, right? So the degeneracy parameter, which we have mainly will deal with D, so we will represent that as a capital D, which is e to the power alpha. And we have seen that if this parameter is extremely large than 1, very large than 1, then you can apply this Maxwell-Boltzmann statistics, or they behave classically. Okay, and other 2 conditions were there, which we will slowly talk about. Okay, so and you are going to see some of the examples as well as the topics that I'm going to discuss in this video, that this degeneracy parameter, either D or 1 by D, whichever comes in the equation that you will see, plays a very fundamental role in quantum statistics. In fact, some of the meaning, what should I say, gas which is thought to be behaving in a usual way, they start behaving very unusual way. Okay, which was not, which led to meaning a very interesting as well as the complicated quantum physics to deal with. Okay, so we'll see something like liquid helium, which will which will behave like a superfluid, okay, which is different from usual liquid, okay. So this will happen because of this the appearance of this degenerate nature of this quantum objects or quantum gas, or you can think about some of this gas which is going to deviate largely from the perfect or the ideal gas that we talk about, okay. So later on we'll talk about this the deviation of energy and deviation of pressure, okay, from the perfect gas using this degeneracy parameter, and then eventually we'll see temperature dependence of degeneracy parameter, and this is going to be heart and soul of this lecture, okay, where you will see you will see a phenomenon which is known as Bose-Einstein condensation. All right, so to start with now, we will know what this about the expression that we have obtained for the most probable distribution of the Bose-Einstein gas. Right? So in statistical equilibrium, we have obtained how the different bosons are distributed in different compartments, right? So that is given by this Ni. This is the number of particles or number of bosons in ith compartment, okay, and it's given by Ni equal to Gi is the number of cells, right, or number of small boxes that we see within the compartments, or number of quantum states that are present for a energy state or energy level, I would say. So then given Gi by e to the power alpha plus beta Ei. So Ei is a Ei or epsilon Ei. So I will I will use these two things interchangeably, so please make a point out of that. And then beta is, we all know, 1 by kT, and then this epsilon Ei is your energy of that ith energy level, and -1. So this we have seen, okay. So thus we have substituted for this e to the power alpha as d, okay, which we will refer to as a degeneracy parameter as we go along. Now here another assumption that we have made, that for a perfect gas the interparticle interaction that we assume to be negligible, or it's not there almost, okay. So the energy that is present, or the energy that we talk about this kind of gas, it's entirely due to translational motion of these gas molecules or particles, okay. So whatever energy present in that system is entirely translational energy, okay. So now we will talk about this number of particle states, okay. So we have talked about density of state in terms of energy, right? This G of E we have talked about. What did it mean for us? It means the number of states that are present in the energy range E and E plus dE, okay. So similarly, same thing just we talk about now in terms of momentum now. So G of P dP represents the number of particle states lying in the momentum range P and P plus dP, okay. So and it is given by, okay, we can work out actually while calculating for this number of states for the energy level range in the E and E plus dE, we have used these expressions, okay. So this is going by the usual way. If you are if you are not finding comfortable with this expression, you can go back to that video and again go through once, okay. Only extra term has come up here. This is GS, so which is spin degeneracy part, okay, which is equal to 2s plus 1, okay. S is the spin quantum number here, okay. Okay, all right. So this is given by G of P dP is equal to GS 4 pi V. V is the volume of the gas which is enclosed in, and by H is the Planck constant, H cube, then P square dP, okay. So this gives you number of particle states lying in that momentum range of the P and P plus dP, okay. So therefore the number of particles lying in that momentum range is given by this expression, nothing else, the same thing. So we have now because these energy states are lying so close, or in fact the momentum states are lying so close, that we can assume these continuous values of momentum as well as energy. So that's why we can replace all this discrete nature to the continuous variables. So the so the number of particles in that momentum range, p and p plus dp, is given by this expression. Okay, where I think it is pretty evident how it has come about, right? So I have replaced gi by g of p dp, d as usual, then E is, so this energy, yeah, so the energy is related to the momentum by this expression, okay? E epsilon, meaning the energy, E, the script E is equal to p square by twice m. Okay, so we have just substituted for that. Okay, now yeah, right, so then your g of p dp from here, from this expression, sorry, so from this expression we can just take out this expression and substitute here, so you will get this expression. Okay, yes, it is given here. So E is equal to p square by twice m. Okay, so now from here, using this the expression, we can calculate what we are familiar with earlier, that number of particles lying in the energy range in the E and E plus dE, or script E, okay, and script E plus dE is given by this. Nothing else, you have to just substitute for now this p square. So p square is, so for p square is given by twice m this E, right? So this term has come. Then you have to replace this dp with, meaning change it to E, right? So your E is given by p square by twice m. So dE will be 2p by 2m. This is dp. You need only expression for dp, right? This 2 will go off. So what you have to do, so m by this p I can write as square root of 2m E, which is dE equal to dp, isn't it? Or I can write this is m by twice E to the power 1 by 2 dE equal to dp, right? That's what I have substituted. See, dp equal to this expression. So this is what I have substituted here. So this part is completely coming from this. Okay, so I think if you're not able to follow, quickly please do this calculation math. And let me tell you, in this video, lots of maths you will see like this, which I will leave it for you to carry out few things, because it's not possible to carry out each and every mathematics here. Okay, so I hope you will do it, and if you're if required, I will give a separate PDF, and I'll upload a text in your Google Classroom as well. Okay, so now you have to just follow the usual math. Okay, so you will get this expression. Okay, you have to just reshuffle the terms here and there, then you have to substitute. Okay, let me clean up this part, then it will be, yes. So what I will do now, this ugly looking, so-called a complicated looking expression, let's substitute with x equal to E by kt, and so the dx will become this. Okay, so wherever these terms you see, substitute with the x, so your expression will become this. Okay, then again you reshuffle, rearrange the term such that you get this. Okay, so you may be wondering how this square root of pi has come. Okay, just to ensure that this is pi. Okay, so I have only one pi, so here you see square root of 3 pi is there, so that's why, so I have to divide by 1 square root of pi, such that eventually I will get a pi. Okay, so from here I have generated like so many square root of pi's and then arrange the terms. Okay, so this is done just to mainly make sure that I get some meaningful expression out of that. Okay, so if I rearrange again, you will see that this term in bracket must be familiar to all of us. How? This represents, so while trying to derive the expression for the continuous, the expression for partition function in continuous variable, right? We have got this expression. You can go back to that video and watch again if you are finding it a little uncomfortable here. Okay, so this expression I will substitute with Z now. Okay, so this term with the bracket is the translational partition, because you're talking about only the translation energy here, right? So this represents the translational partition function. Okay, so now you see the expression become little simpler. Okay, so after substitution for x now. Okay, so here most important part you will see here, this d parameter. Okay, d is what? E to the power alpha. Okay, so and keeping all the things intact, now this the number of particles lying in the energy range E and E plus d, E is given by this expression. Okay, what is x? E by kt. Okay, so now the total number of particles, what I have to do, simply integrate out from the 0 to infinity. Okay, because energy, let's say from the 0 all the way goes to infinity. So you have to carry out this integration, right? So nothing but, so this integration has to be, so other things are constant, right? This 2 is number, gs is a spin degeneracy factor, that is constant, z is partition function, root pi is constant. Only thing is that this integration has to be carried out. Similarly now, for the total sorry, this should not be total, just simply total energy. The total energy is given by this expression, right? So so the energy of meaning the each of this level, and then how many particles are there in each energy state, and then integrate of all these things. So substitute for this E in terms of x, I will get this, right? Because x was equal to E by kt, right? Okay, so now again what you have to do, simply substitute back. Yeah, so you have to substitute for the this dn, right? So you have to substitute for this dn. So whenever you get dn, see this, for dn there is a term x to the power half. So you have one more extra term here, x. So this will be x into half. So that's why you get x to the power 3 by 2, isn't it? So now your main aim is to here, right, to get total number of particles or total energy of the system. What you need to do? You need to carry out these two integration. That's all you need to do now. Okay. So while doing so, so the idea is to evaluate these two integral. Okay. So we have to use some separate tricks. You may be familiar with few of them. Okay, I mean, in fact, you will use only one way to solve. Okay, and you will see what we get. Okay, so idea is clear, right? So we are trying to find out so in the beginning we said that, so we are trying to find out deviation of energy of this Bose gas or Bose-Einstein gas from a perfect gas. So later on, after we study that, then we will try to understand the deviation of the pressure of this Bose-Einstein gas from the perfect gas. Okay, so on the way now we are stumble upon these two integrals, right? So idea is to solve these two integrals. Now how do I do that? In fact, I will do it for one, and you will see you can carry forward the mathematics for the second integral. Okay, so now if you take this integral and in the denominator you take this d e to the power x common. Okay, so you will remain with this expression. Take this to the top, right, in this fashion. Okay, all right. So here now what you will do, take this expression, the binomial expansion for that. I hope you all are familiar with this. Okay, binomial expansion. So this binomial expansion is introduced in the class 11th, okay, in mathematics part. So you must be familiar with this maths. Okay, so then while using the binomial expansion, okay, of this expression 1 minus e to the power minus x by d, what will happen? Simply it's like 1 minus x whole x, so it will give you 1 plus x square, and then keep going all this. Okay, so there is a factorial term, but everything is 1 here, so then you need not worry about all these things. Okay, so this binomial expansion of this term will give you this result. Then what will happen? Use the properties of integration, right? So simply multiply this each term to each of this term, or this whatever the we have taken common to each term, right? So let me clean it up, then you will see better. Yes, so I will remain with, so multiplying the first term with the 1, I will get this. Second, this term with the multiplying with the second term, you will get this. Okay, so now this has got certain, so it will keep going. Third term, you can write 1 by d cube, right? and 1 by, so let me just write, so probably 1 by d cube, then integration will be 0 to infinity x to the power half e to the power 2, this is minus 3x dx. Okay, it will keep going like that each and every term. Okay, so now I will use standard integral. Okay, so I, for this integration, integral I need only this, so this I will be using later for the later integration. So you see, for integration from 0 to infinity x to the power half, meaning 1 by 2, then e to the power minus nx dx is given by this. Okay, square root of pi by 2 into n to the power 3 by 2. So what will happen now, for each term let me substitute this value. Okay, so while doing so you will get this expression. Okay, isn't it? So the 1 by ds was common, so root pi by 2d 1, and then 1 d square will come, d cube will come as you keep going. Okay, so you just carry out, you just substitute for each term, you will see this expression will come up automatically. Okay, it's not complicated. Now similarly for the second expression, meaning the second integral that we have to solve here, this integral, you have to follow the same technique. You take common this d into e to the power x, then this binomial expansion you keep doing, or each and every step you can copy and paste. Only thing is that the exponent in the x will change. Then you use this standard integral formula for the standard integral, then you will ended up getting again a similar kind of expression, a infinite series of integrals, let's say. Then using the values of this standard integral, then you will get this expression. Okay, so I'm not going really deep into each of this integral. I hope you can carry out this, and if not, put your comments in your Google Classroom. If required, I will carry out each of these steps separately. Okay, in a separate PDF I can upload. Okay, so now what you have to, our idea was to how to find out the total number of particles and the energy of the system. So now substitute back the values of the integrals that we have to obtain, this one and this one. So this second expression will be requiring for the energy term, and this is required for the total number of particles that we are trying to find out. Okay, so here see, this is, there are 2 by square root of pi, right, gs and z. So this 2 pi right, square root of pi by 2, this term will get cancelled out pretty easily. Okay, and I will remain with this. Okay, now this is one of the very important expression, you must write it down or note it down. Okay, so if we assume it for only, let's say, if your d is really large, if we retain only up to the first term, so your n number of particles will be given by, is it gs z by d. Okay, so why am I writing this, or why am I putting little attention to this? Because I will be using of this term. Okay, now similarly for the energy term, you have got this. Okay, now see, here I have to make one thing, this has to be -1, has to be there. Okay, now substituting for gs from the earlier expression, so what I have done here, so this gs, gsz here, see the gsz from the, so here let me write it down. Okay, so this expression is what, n equal to this, so gs will be equal to what, so gsz will be equal to n d, and then whatever there in this entire bracket, okay, to the power -1, right, isn't it? So within the bracket, this entire 1 plus 1 by 2 to the power 3 by 2 d plus entire this infinite series expression will come here. Okay, nd by, yes, so nd by these things you can, okay, nd multiplied by this expression to the power -1. Okay, so that's what we have done. So this, because there were this, so I'll substitute for this, right, gs term in this. So this d and d will get cancelled out. So this d and this d will get cancelled out. So that's why you don't see any d here. And this n, which will remain, this n here, kt comes from here. Gs has been substituted, d is being here. Okay, so this expression comes from this as usual from the energy expression term, and this is the term comes from the gs and to the power -1. Okay, so let me again clean it up and okay, sorry, so this minus 1 has to be there. Okay, so this minus 1 has to be there. So okay, so now again I will do a binomial expansion of this second term, this term. Okay, what I will do, earlier we have done it, right? So it will be simply you put minus sign on in front of all of this except the one, the first term. Okay, so now what you have to do, so both are infinite series, so these are product of two infinite series. What you have to do, just calculate few terms, then you will know. Okay, so here I leave it to you to find out that this is indeed true for the at least 2 or 3 terms. Okay, first 2 or 3 terms. So I have calculated out, so that's why I have written out. Okay, so if you need, I can give you the PDF if you want. Okay, so what you have to do, first you take this one and this one, so I will get 1. All right, then you multiply this expression with 1. Okay, so anyway d is there, so you can, so you will have plus 2 to the power 5. Then again this term you multiply with this 1, isn't it? So then you will get minus 1 by 2 to the power 2. Okay, and this 1 by d is anyway common, so that will come, and if you carry out this math, you will see that this is indeed minus 1 to the power 5 by 2. Okay, so then you substitute back here. So you will see that the product of these two infinite series will give you another infinite series with this expressions or these terms. Okay, so you will be ended up with the expression for energy given by this expression or as it shown here. Okay, so now let's say we take, right, so if we substitute for, considering up to only the first term in the equation of d, yes, so this was I have thing, so I need to substitute for this 1 by d expression. Let's say 1 by d. Okay, so 1 by d is given by what in this, which I have, if I take the expression of n is only for the up to the first term, so 1 by d is given by, it will be n by gs by z, right? So now if I take that, so I had this 1 by d here, right? So 1 by d is what? N by gs z. Substitute for each term, I will get this. Now what I will do, let's consider n is equal to 1 mole of gas. Sorry, it's not n, so n is going to give me total number of particles. So if let's say gas for 1 mole of gas, so the considered gas is like 1 mole of gas. So how many particles? Avogadro's number of particles, right? So 6 point, that number, 6.6 into 10 to the power 23 number of particles. Okay, so then so that Na, this Avogadro number multiplied by K is going to give you the, so the Na Avogadro number multiplied by K is a Boltzmann constant, is going to universal gas constant R. So for 1 mole of gas, I will get this term equal to R, T as it is, and this entire infinite series expression I write it simply eta. Okay, now here point to learn or point to note here. Okay, so if we, let's say our degeneracy term is extremely small, so I can ignore this part. So I will remain with what? Energy equal to 3 by 2 RT, which is energy for a perfect gas. So whenever this degeneracy term, this is n by or a 1 by d or n by GSZ is going to make a significant contribution, you will see that we have to add term after term, and then gas will slowly deviate from the perfect gas. So this expression tells you that. Now, okay, so this is about the deviation of energy from a perfect gas. So it's given by this eta. So the eta term you have to remember, okay, this entire expression. So if you have more and more contribution from the eta term, you will see that energy is going to get reduced from the perfect gas or an ideal gas. Okay, so this is the way to see the deviation of the Bose-Einstein gas from a perfect gas. Okay, now let's